Okay, guys. So today what I'm going to talk about is Haworth projections specifically for ketoses. This has been a little bit of a difficult, part, I think, for some students. So I'm going to do a couple examples of specifically with ketoses. First, I'm going to start by talking about how we do Haworth projections of aldoses. So remember, if you have an aldose like this, I'm just going to make one up. And of course, I start off by making ketose. An aldose, which starts with you have the aldehyde on top. All right, so and I'm just going to sort of randomly put the OHs according to my whims right now. And so when we know that we're going to get a ring. We're always either going to get a 6-membered or a 5-membered ring. And so the trick is figuring out which is which. So when you get what you want to do is you want to find the carbonyl carbon. For an aldose, it's the one on top with the CHO here. So this is 1, 2, 3, 4, 5. And the last the OH group, the hydroxyl group in the last chiral center is going to be part of the ring structure. So we have 1, 2, 3, 4, 5, 6 rings. So this is a 6-membered ring that we get. And so what we do now is we look to see if it's D or L. So we look here. This is D. So we deal with this last chiral center first. So if it's D, that means the CH2OH group is sticking up, not down. So that's what D indicates. Now this first chiral center here, this one, number 1, is depending on whether we get an alpha or a beta, it could be either up or down. So remember, this is the chiral center that is made, which becomes a chiral center upon making the ring. This is this carbon here. It's not a chiral center at the beginning. So whether that OH is up or down depends on the orientation of the aldehyde group at the moment the ring is made. So it can be one or the other. Now we start here. So this is carbon 1, 2, 3, 4, 5, and 6. I'm going to do 1, 2, 3, 4, 5, and 6. So carbon 2, we look at the chiral center. Now this is where we see if it's on the left-hand side, then on the Haworth projection, it's sticking up. So number 2, up, because it's on the left. 3, it's on the right-hand side, so we're going to go down. And then number 4, it's sticking up because it's on the left-hand side. Number 5 has already been taken care of at the beginning. When we drew the CH2OH sticking up, the reason number 5 is not dealt with, so this is carbon number 5 here, the reason it's not dealt with by drawing an OH is the O actually ends up here. So we have to show it another way. We have to show it with carbon 6. So that's an aldose. I'm going to do one more example of an aldose to show you something important here. I'm going to show an example of an aldose that only has 5 carbons in it. So here it is, CHO, 1, 2, 3, and then I made it too long. Let's do like that. Now, when we count, we're going to do exactly the same counting method. I'm going to start carbon. There's 1, 2, 3, 4, 5 things in the ring. Now, I don't want it to get confused. We're still counting the carbons like 1, 2, 3, 4, and 5. That's how we're counting the carbons. But notice there's 5 things in the ring, the blue dots. There are 5 blue dots. So I'm going to have a 5-membered ring with an oxygen on the top. Because it's D, we look at carbon 4, the last chiral center, the one at the bottom, to determine that it's D. Since the OH is going to the right, that's a D. And so on the Haworth projection, we stick the carbon going up. So carbon number 5 is sticking up. So this is carbon 1, 2, 3, 4, and 5. Carbon number 1, again, that first one, the hemiacetal carbon, is always up for grabs. It depends on whether it's an alpha or beta form. And remember, it's in equilibrium. It can shift in and out of alpha and beta. It can shift between them. Carbon 2, we look, it's on the left-hand side, so it's going to stick up. It's on the left-hand side, sticking up. And then this one is already taken care of. We already did that one. So the best procedure is to figure out how many things are in the ring, do your last chiral center based on whether it's a D or L enantiomer, deal with whether it's an alpha or a beta, and then assign the rest. So let's move on to what I was actually wanting to talk about, which is ketoses. Ketoses are a little screwier, a little bit weirder. So let's look at ketoses. So ketoses have this. Okay, so we're going to start, as always, with the carbonyl carbon. So it's important to understand that now the ring starts with carbon 2. So this is a 6-membered ring, but the ring starts forming on carbon 2. So the ring only includes carbon 2, 3, 4, 5, and then the oxygen. Another thing to understand is the oxygen in the ring, I'm going to emphasize this again, this is the oxygen that's actually in the ring, not this one. Okay? So if you count the blue dots, 1, 2, 3, 4, 5, there are 5 things in the ring. So I'm going to make a 5-membered ring. This is a little bit different from the aldose, though. This structure has 6 carbons, but it's only a 5-membered ring. So what happens is, let's start where we always started. Let's start with the last chiral center. So this is a D enantiomer, right? 5. This last chiral center tells me that because the OH is going to the right, that it's a D enantiomer. So on the Haworth projection, we show CH2OH. The first chiral center, again, depending on whether it's alpha or beta, will be here. So remember, alpha means that the two, so if this was an alpha form, then this would be going down. The things that we're talking about being opposite are the first OH group and the last carbon sticking up over here. So if it's an alpha form, then we have the OH going down. But also it's important to understand, coming off of, so this is carbon 2, 3, 4, 5, and 6. So it's important to understand also coming off of carbon 2 is carbon 1. So it's going in the opposite direction of whatever the OH goes. We still call this alpha because the OH and the CH2OH, these two things are opposite each other, but this just fills up wherever the blank is. And now we follow the same procedure as before. I look at carbon 3 here, and I see that this OH is going to the right, so it goes down like that. It's going here, it goes down like that. Now, if we had the beta form of this, what happens is the OH and the carbon 1 swap places. This is the beta form. So I hope that helps a little bit. The main thing to remember is that in both aldoses and ketoses, what's included in your ring, you start at the carbonyl carbon and you end at the last oxygen on that chiral center, on that last chiral center.